There's a relationship between change in momentum and a quantity called impulse. So to show you that, let's consider a single mass m being acted on by a constant net external force F. So this would then represent a force diagram for the mass m. I'm assuming that the net force acts to the right, but it could be acting in any direction. So whatever the direction of that net force is, there's going to be some acceleration in the same direction of that force, and the acceleration by Newton number 2 is going to be the net force divided by the mass. And let's say at the beginning of some time interval, um, little m has a velocity v sub I standing for initial. I'm, for simplicity, assuming that that points in the x direction, and let's say it has a velocity v sub f, final velocity, and again for simplicity I'm assuming that that also points in the x direction. So if you look at your kinematic equation cards, you will recall that there is a kinematic equation, it's the first one in your card, which relates the final velocity in the x direction to the initial velocity at the x direction, and the acceleration in the x direction, and time. And so technically speaking, I should put a little sub x right here. So for the situation we want to consider, we want to replace v sub x with v sub f. That's the final velocity. Vx naught gets replaced with v sub I. And t gets replaced with delta t. This is the increment in time between the initial and the final velocity. Then we can take the acceleration, and by Newton's second law replace that with f over m. We can put v sub I over on the same side by subtracting it on both sides, and what we get then after a little bit of simple algebra is mb sub f minus mb sub I is equal to f times delta t. On the left we have the change in momentum, and on the right we have a quantity called f delta t, which is known as the impulse. So whatever the direction of the change in momentum, the impulse is in the same direction. Momentum is a vector, and so is impulse. In terms of units, momentum has units of kilogram meters per second. Impulse has units, as you can see from f delta t, of Newton seconds. And if you break newtons down, you will see that Newton seconds are, in fundamental terms, the same units as kilogram meters per second. So in the previous YouTube, we talked about a situation where the external force was 0. And in that case, remember, we said that momentum was conserved. Well, if the external force is 0, the impulse is 0. F here represents the net external force. And in an isolated system, the net external force is 0. And so if you have a situation where the net external force is 0, this same equation tells you that f delta t is 0 and that the change in momentum is 0. And if the change in momentum is 0, momentum is conserved.